In question 2 of this series, I'll show you how to find the derivative of polar curves. Remember that to find the derivative of polar curves, you use the following formula, where dy over dx, the derivative, is equal to dy with respect to theta over dx with respect to theta. So what we have to do is convert this polar equation, that's in terms of r and theta, into an equation that's in terms of x and theta and y and theta. And then subsequently find the derivative of both of those equations. If you're confused by that, here's what I mean. I'll first take the content of r, which is the right side, and place it right into here. That will give me an equation that's in terms of x and theta. Look, x is equal to, taking this and placing it right into there, cosine squared theta plus e to the power of 5 theta, all multiplied to cosine theta. Similarly, I'll do y is equal to the same thing, cosine squared theta plus e to the power of 5 theta. And placing this expression into here, we end up with sine theta. Next, what I'll do is find the derivative of both of these equations with respect to theta. Let's start with the first one. The derivative of this equation can be represented as dx over d theta. And we'll start by finding the derivative of this factor and then multiply it to cosine theta plus this expression times the derivative of cosine theta. Let's go ahead and do that. The derivative of cosine squared theta is 2 cosine theta. Subtract this 2 by 1. And the derivative of cosine theta is negative sine theta. Plus the derivative of e to the power of 5 theta is plus e to the power of 5 theta times the derivative of 5 theta, which is 5. I just found the derivative of this factor, and I'll multiply it to cosine theta. Now I get to find the derivative of cosine theta, which is negative sine theta times this expression. That takes care of the derivative of our first equation, and now our second equation. The derivative will be dy over d theta is equal to, remember, the derivative of this expression was already found, and it's right here. And we'll write down sine instead of cosine, plus the derivative of sine theta, which is cosine theta, times this expression. Now that we found dx over d theta and dy over d theta, I can place that into here. Dy over d theta goes on the top, it's the numerator. And at the same time, I'm going to try to clean this up as much as I can. Instead of it being written like this, I'll write it as negative 2 cosine times sine theta plus 5 e to the power of 5 theta sine theta. No need to expand. I'll just make it more messy. Plus cosine theta and the rest. All over. Now I need to rewrite this underneath, but I'll clean it up as much as I can. I get negative 2 cosine theta sine theta plus 5e to the power of 5 theta multiplied to cosine theta minus, I'm combining these two symbols, cosine squared theta plus e to the power of 5 theta. This right here represents dy over dx. Now, the question says, what is the instantaneous rate of change at pi over 2? So now I have to apply pi over 2 everywhere where I see the theta. Now remember, instead of doing this all on your calculator, you can sort of be logical here. What is cosine at pi over 2? In other words, what is cosine at 90 degrees? At 90 degrees, cosine is equal to 0. What about sine? Sine pi over 2. Remember, the sine function looks like this, where at 90 degrees, it's at 1. So, negative 2 times 0 makes all of this become 0. This becomes a 1. This all becomes a 0, and this all becomes a 0. This becomes negative 1. So we have 1 times 5e to the power of 5 theta, which is 5e to the power of 5 theta. So our numerator is 5e to the power of 5 theta, this becomes 0, and over here, this becomes a 0. Negative 1 times e to the power of 5 theta gives us negative e to the power of 5 theta. If I apply pi over 2 into here, and pi over 2 into here, I'll end up with negative 5, because this cancels out with this, and 5 over negative 1 is negative 5. And there you have it. That is how to find the derivative of polar curves.